colleague Chee Chiang here. Okay, thank you.
Hi, this is Chee Chiang from NUS. I will present on the topic on the cycle harvesting grid for research computing. Just hold on because I can't get my slide moving. Okay. This is an overview of the presentations. Basically, I will focus on the strategic role of cycle harvesting in the use of this technology to address some of the research computing requirements. Some application example will be given, and also we will go on to explore some collaboration opportunities. The next slide shows some of the computational research requirements that we are facing today. I believe all these requirements are quite common in most of the research universities around the world. For today, we will focus mainly on the use of the cycle harvesting grid technology to support and also to address the massively parallel computing requirements, which include the large-scale data parallel processing, as well as the parametric study type of research applications. So this will be the focus on today's discussions. Next slide, I will demonstrate how the cycle harvesting grid work at our site here. I hope you can see the cursor that I'm showing. For all the nodes and PC and servers that are connected to this cycle harvesting grid, grid agent will be installed on each of these systems. And this grid agent will actually monitor the load level of all these nodes. Once the PC or the server is idle, the agent will actually request a task from the grid server to request for tasks to perform. When the grid-enabled application is submitted to the grid server, the job will be break down into a small task. Each of these tasks will be sent to those agents that are requesting for a job to perform. After the job has been completed, the result will be then sent back to the grid server, and the user can then retrieve the result from the grid server. That's how basically the cycle harvesting grid work. Just give you a better idea of how a grid-enabled application work in this environment. This is the image rendering software called Porphyry, which has been grid-enabled on this environment. When a picture is being sent to the grid environment to render, the pictures will be break down into a multiple small tasks. Each of these tasks will then be sent to each of the grid nodes to perform. After the completion of each of these small tasks, then the result will then send back to the grid server and put together into the complete pictures for the user. With this cycle harvesting grid processing, basically we can reduce the processing time from 20 hours on a standalone PC to about 2 hours. This may look trivial when you are actually rendering only one pictures. But imagine if you have to render 10 minutes of video, for example, with maybe about more than 10,000 images, then this grid computing resources will be very useful. The following slides basically display how what is the strategic role of this cycle harvesting in our computational research computing support. As you can see here, the cycle harvesting grid is being used to harvest either cycles that we have today. The main purpose is actually to create new research computing capability by aggregating the existing distributed and also diverse computing resources, around campus. The other benefits of this, of course, is it also helps to maximize the compute resource utilization across the campus. And this, as you can see from the slide, the resources can be harvested from not just the compute server, but also more than 1,000 PCs across campus at NUS today. Today we have about 1,300 PCs and also about 1,250 server CPU cores available on this cycle harvesting grid. We also see there's a great potential of this cycle harvesting grid in the future development of research computing support. Basically because this cycle harvesting grid is, as I've shown with some of the example, is very suitable for data-intensive and data parallel type of applications. And we can see many of these applications can be found in areas such as biomedical sciences, signal and image processing in engineering and science. We also have some application in financial engineering and modeling and social sciences as well. We also see there will be more opportunity for us to harness either cycle from PCs and from server, simply because we see more and more system will come with multi-core setup, which actually increase the opportunity for you to harvest on all those either cycle, because most of the time not all the cores can be used by the owner or the local user. And you also see there will be advancement in the network performance, which is actually very critical to the grid applications. Just give you some example of how we use the cycle harvesting grid at NUS. This is the application in financial modeling. You can see some of the job that we have performed actually has been reduced from around a month to basically 1 or 2 days kind of computing time. Of course, this is not the best speed up we ever achieved. In fact, the record speed up that we have achieved in one of the bioinformatics applications was about 200 times speed up for a single applications. And also to highlight here is that some of these applications or jobs can be performed in parallel because we have enough number of nodes in the grid. So multiple jobs can actually be performed so that it will actually help to speed up the application even further. This is another illustration of how the financial modeling application I mentioned earlier, how it was actually break down and distributed to run on this cycle harvesting grid. The second example here is on the biochemistry applications. Here, even larger type of computation has been performed in this cycle harvesting grid. As you can see in those highlighted jobs that you see on the slide, one of them actually, if you perform on a single CPU, it will take about a year to complete, and the computation time has been reduced to about a week for that particular jobs. The third example here is on the another biomedical or life science type of applications, and again, we managed to achieve quite a significant speed up in this area for the researchers. The final example here is not really a scientific applications, but it's more on applications performed by a startup supported by the university, which are actually processing some patent images, to make them available on on their web portal, so that for people to search and compare, to search whether certain pattern has already been registered so to do this kind of image processing, they need a lot of computing power to generate those images, and they, in one instances, they actually generated about 8.8 CPU years of usage, in 3 months. Again, this is not the maximum type of resources we can generate from this. We managed to generate about 17 CPU years 2 years ago using one of the bioinformatics application in 1 month. Okay, next we look into the what kind of opportunity, collaboration opportunity we have, and what are the challenges we may face. For the cycle harvesting rate, the more nodes, the more PC, the more server we can connect, the greater computing capability we can create. So there's opportunity for us if there is opportunity for us to link up more and more PC and nodes, then it will make the cycle harvesting grid more useful. Of course, to do that, we have to address the licensing issue, because we are actually using a commercial software for this grid enabling, and also it will also depend on network bandwidth as well as getting more and more users to use it. So the next two slides, basically you can reference, basically showing two of the options that we can actually share resources in this kind of environment. Yeah, that's all for my presentations. Thank you.